we are now in a configuration B. It means waves interacting with a floating structure with vertical walls, and we consider waves model with dispersion. Brief recap of past lesson. First, we need to divide the wave propagation into two areas, the exterior one and the interior one. It's very important to separate them because they are constrained differently. The exterior part, we have one constraint on the surface pressure, which must be equal to the atmospheric pressure, equal to 0. So there's enough general. And in this case, the surface elevation, zeta, is free. It's the opposite in the interior domain, where the surface elevation is constrained to fit the bottom of the object. It is written here, where delta is the dynamic of the solids with the difference between the center of mass and its equilibrium, and zeta E at equilibrium is the parametrization of the bottom. For sake of simplicity, we will consider that this is a flat bottom. In that case, the pressure is now an unknown, and we will see it at a Lagrange multiplier. I written the Boussinesq equation, which is here, in the exterior domain and in the interior domain. And if there are too many equations, just follow the colors. Everything which will be in the exterior domain will be in blue, and in the interior one, in red. And I put in purple something which will be the transition between the interior and exterior. Purple is the mean between red and blue. And first, as you see, David explained, since it's constrained differently, the real variable in the interior domain is not the fluid variable, but other variable. I mean, you see that the surface elevation is given by, this is no. This is given by the dynamic of the solid. If I plug this condition in this one, I know that the interior discharge is exactly minus x plus these things is the average. Perhaps I can take something for notation here. I recall that this guy is the average between one contact point of the solid, is this one, minus the contact point here between the exterior and interior area. Oh, sorry. Then you see that if I know delta and the average of the discharge, I know all the fluid variable. Here, I can see this equation, not an equation like in the exterior domain on the fluid variable, waves variable, but something on the pressure. So I just plug this equation in this one. I recall the flux is where the water column H is 1 plus epsilon zeta. Of course, I work with n-dimensional system. It's why with David, you see H0 plus zeta. Here, with n-dimensional variable, I must introduce a nonlinear parameter epsilon, and it is given here. So, just plug this equation in this one. First, you see that since this guy have only one, it's x, the second derivative don't act. So even if I consider Boussinesq systems, here in the interior region, the dispersion don't play any role. It's like classical shallow water equation. So I just plug here. So I have where the dot means the derivative with respect to time. I said that here it don't depend of x. I have a flat bottom. So if I derive this guy, it's only given here by the discharge, which is this guy. So I've, at the end, if I don't do any mistakes, so it's an equation on the pressure, but to solve it, I need boundary condition on the pressure. I have not, but it's because the system written here is not yet complete. I've not given any transmission condition between the exterior area and the interior area. One, it's known, it's given by the conservation of the volume, which implies that the discharge must be the same as the contact point. The second one, it's more difficult. In the configuration A that studied David, there is a non-vertical wall, the curved wall, and he says that the surface elevation must be the same because it's a curved wall. Here, it cannot be the case if you see that the height of the water column here is given in blue, and you see that if I put in this case, you see that it cannot be necessarily the same. So what can I put for the second transmission condition? We choose one arbitrarily, which makes the conservation of energy. I say arbitrarily, but it's physically relevant to want conservation of energy. So it's what now I will show you how I can link conservation of energy and boundary condition on the pressure. So first, what is the energy of the solid? The energy of the solid, you see Newton equation. Oh, I say Newton equation, but you see, as I say, I work with n-dimensional variable, and it's why you see an 1/2L. And it's not really the mass, it's a non-dimensional mass. The energy of the solid is given by, here it's because I normalize with 2L, and kinetic energy plus potential energy, it's delta. If I derive it with respect to time, I have sorry. And I use Newton now. It is, see this guy, so it is exactly. Now, for the fluids, I say Boussy, for Boussinesq. As David explained, the energy is this one. Yes, I had one term that David doesn't have. It's because I consider dispersion in the Boussinesq model. Okay, and before derive this energy with respect to time, I just want to underline that Boussinesq system has local conservation law. It will help us. I say local, but it's more complicated. If I introduce local energy, which is here, I don't put colors, you see, because it's both in the exterior and interior area. Here, I must put color, but it's in red. Of course, I forgot all. I've introduced a local flux, which is, I don't remember exactly the expression. I say that the dot is derivative with time. There is both here. And both are linked to a local conservation of energy, but when there is some pressure, it's not a conservation of energy. Plus, in fact, there is, I don't want to put some details now, perhaps after I will explain you, that there is, we don't have really conservation of energy. We have here a terms. It's because Boussinesq system don't really conserve energy, but it conserves energy as the order of magnitude of this model. I mean that this model is valid in the sense that it's a good approximation of Euler equation or water-weight system, the one that Thomas showed you last week, at this order of magnitude of the system. I don't give you the proof because it's only computation and it's quite boring. So now, if I look for the total energy, of the system, I say it's the sum of the solid energy plus the Boussinesq energy, but in the interior domain, plus the Boussinesq energy in the exterior domain. I want to derive it with respect to time. So I have the one here, it's all compute. It's this guy. This one is the integral on the interior area of the local energy. So it's given by it's given by this guy. Of course, plus the other term, which is sorry, and I have this guy. Plus, of course, one term that I don't want to explain, but it exists, but do it like it's a negligible term. And after, I have the same of this guy, but in the exterior domain. And in the exterior domain, as I say, the pressure is atmospheric pressure. It's null. So you just have this guy on the exterior domain. remember that the interior discharge is given here. And when you derive with respect to x, you have only the velocity of the solid, which is exactly compensates the solid energy. So this one. So in conclusion, we have that is exactly, I'll put another notation. Use here the average between the average is between and I call also introduce for any function the jump, which is the difference between what happened at the contact point at the left and at the right. And so here, if I integrate this guy in the interior domain, you have something what happened in x plus and x minus. And here is the opposite. And if you assume that you have enough, for instance, enough regular solution, what happened in infinity shrink to 0. So it's why at the end I have, where is my colored key? Yes, 0. The flux, so we say, okay. I say that I want conservation of energy. In fact, it's not conservation of the energy, it's conservation of energy at order of magnitude epsilon kappa square. So what can I put here to have a conservation of energy? If you see the expression of the flux here, you can say that, oh, if I choose one typical value of the pressure at x plus and x minus at the contact point with respect to this variable, I can have conservation of energy. I mean that if I choose for this conservation of energy this value of P at the contact point, I need to see this guy. The code of colors can be sometimes very long, but it's, oh no, I forget the square. And the last coefficient here, it's okay. You see, if I choose this guy at the interior pressure, you will see that this guy will be 0. Plus, I recall something that I don't want to talk. So now I've complete the system, and you see that I can link. Oui, yes. H is 1. H is it's the same. It's H is every time 1 plus epsilon zeta. And here at the boundary it's 1 plus epsilon zeta in blue, and here 1 plus zeta in red. So if I put together I have one equation on the pressure. Now, I would like to plug this equation on the pressure in the Newton equation, and I also would like to integrate this equation on the pressure in order to have some equation which only involves the movement of the solid and the average of the discharge in the interior domain. So, as I say, no, just look for this equation. Put one name, it's equation 1. I just want to integrate 1 and divide by the water column and the interior domain. It's simply just when I put this notation, I mean, of course, is the average over the size of the solids. I don't say that. No, I don't say that I put the solid here. It is in 0 minus L plus L. The contact points don't move because we are in vertical walls case, and we only have vertical movement. So continue here the computation. I just plug this guy. No. So what? Oh, and here it's exactly it means it's the average, the jump of the pressure. Here, since I've only considered solid with a flat bottom, here you have event function. And this one too. So at the end, you have one equation on this guy. It means that sorry, I forgot to put in red. Plus, and you see something which a function which depends here on so this variable, and you see hi, it's 1 plus zeta I, and so it's dependent on delta. So you have one function here, I say E1, which is simply this guy. So here, I have one equation that involves the average of the discharge, and a source term which is related to the pressure at the interior domain. And I recall that the pressure at the contact point is given here by something which is related to the waves variable in the exterior domain. Now I can plug this equation in the Newton system, but perhaps before, if, no, there is no if, he asks something about the, okay, we have a, David, you introduce, I don't remember, you introduced Bernoulli pressure when, or the pressure? Bernoulli, okay. So, in that case, sorry, David introduced Bernoulli pressure. Oh, I put the notation here. I can introduce two, in the interior domain, the Bernoulli pressure, which is, in that case, something like that. And so, since I take the case of a flat bottom, here you see that it's exactly the Bernoulli pressure, and here you have the same equation than David in the case A, but you remember that in David's case, the coefficient here depends of one equation related to the contact point. Here it's depend of delta. So it's a little bit different. Now go to the Newton equation. And I can, at the equilibrium, Newton equation is given by Archimedes principle, which is simply the pressure at equilibrium. And then the, this pressure at equilibrium is given by this guy. And so, get finished. By definition, this guy is exactly zeta I minus minus the solids. So I put both together. I have something like that. And it's exactly what David called the Bernoulli pressure. I want to integrate by parts, but I just here it's one, it's the same. And I just want here to integrate by part. I have this guy minus this guy. Oh, sorry. So it's 1 over 2L. And this guy is here, since we have centered the solids, it's just given by the average. Oh, sorry. And this guy, I just want to plug the equation on the interior equation, the equation 1. And so I cannot see the equation here. Here it is. Oh. I write here. It is up. So it's the opposite of that case. It is this one that are even function. And you see here something important, that when I plug the equation of the interior pressure, I have one term related to the acceleration of the. So it's something which acts like a new one called an added mass. It means that when the fluid moves, he must accelerate his own mass and something other, which is, for example, here, this guy, which is related to the pressure that will be exerted on this body. So in conclusion, I have the same. I have one equation, and I put something here for the mass, plus another function. Which is now related to so if I continue here, I read sometimes I don't think it's a necessarily good idea what I do. So here you have the equation. So no, it's not a good idea. So you imagine that this both equation I must write here for the final scheme and say, okay, you see that I've already finished because I have a complete set of equations. The movement of the solid and of the discharge depend now on the Bernoulli pressure, which is given here by this value. But value, you see something happens is that there are this guy who will appear, and it's related to dispersion. You have something with the leading order term. It's two derivatives on zeta, and it's one difficulty that I must take care. But recall, I don't need. Recall that yesterday I show you that we can, in the context of boundary value problem with Boussinesq system, I show you that we can return the Boussinesq equation in the non-local conservative law. And at the end, I say, okay, and can also this non-conservative law implies hidden equation on the trace on zeta at the contact point. So it will be now the way to close the equation and replace the leading order term in this system by a new equation. So I recall the theorem of yesterday, and recall if U, sorry, it's blue now. If I write U as zeta Q, it satisfies the following equation. Where it's not visible from here. It's not visible. Oh yes, the blue is not visible. Okay. So I write in a white, but you imagine that the white is blue. The red, you can see the red or not? Yes, okay. And so you remember that yesterday I say I can write this as a non-local conservative law with connected with the boundary condition. Here, the boundary condition is given, it's equal by the conservation of the volume of the value of the discharge at the interior domain. So that's what I put here. Oh, here, it's not in 0, it's L. This guy, it's a non-local flux. And it's given by Q and R1 zeta, where R1 is the inverse of the dispersive operator with Neumann boundary condition. It means that, if I want this system, you have now it's not only boundary, it's plus and minus. And here it's for the exterior domain. It's for both sides of the exterior domain. So it was shown yesterday. And now we want to use it in order to have a hidden equation, hidden in the sense that it's inside this equation, there is one equation on the trace of theta. So corollary of this theorem, you have, how I can write it. You see the purple or not? Yes? Okay, perfect. If I call this guy, it is the trace plus and minus. It's the trace of zeta at the exterior domain at the boundary. Thence, I have one equation. Okay. Plus and minus over 2 finally plus something you don't see blue, so proof. It is what yesterday we don't do. it's simply, as I say, it's simply a consequence of this guy. I write the second equation here, which is Q plus I do it only for the one side, and the proof will be the same in the other side. Here, I want to derive it with respect to x and multiply by kappa square. It means that I have something like that. And here, I just derive minus 1 over kappa. It's a point, sorry. And I've multiplied here, so I have kappa now this guy, you see the first Boussinesq equation, it's simply minus kappa square zeta derivative with time 2 times. One here, and delta x q is delta t zeta. This guy is simply, by definition of this operator, is simply these things. So I have one equation, and I take this equation when x go to plus L to take the trace. One equation here, which is, yes, I take 4 minus, so I have this good things? No, sorry, I invert here. This guy, you know that it is and so you have minus R1 this guy. And if I take this guy at x equal L, this guy is 1. And so I've just, sorry, G for yesterday. Forgot that. So it's the end of the proof. It's very important because you see that the value of the discharge here is related to the acceleration. It's the time derivative here. So it's related to the acceleration of the solid and the time derivative of the average of the discharge. So I can couple this equation with these two equations together, and I have a big system with a lot of unknown. This one, and one trace at the left and one trace at the right. And I have a big system now which couple all these variables to this guy. Which is connected to what happened in the exterior domain. So, to conclude, here, all the things in the interior domain give me a big system. When I say a big system, it's a system I take here because it is the Horn mass plus the added mass we give. This. Now it's put a tilde because it's a different one. It depends of plus you see, sorry, you see in this guy it depends here of the interior pressure, and the interior pressure depends here of the trace of zeta at x plus and x plus L and minus L, and of the interior discharge, and of the interior surface elevation, which is connected to delta and QE. So I have something like that. Minus I have also another equation. I'll show you. It's the same variable. And the last system I show you plus say you don't really need to know what is in this coefficient. It's what we have computed, but the only interesting things is type of system plus, this is this equation, is exactly this one. I must replace this guy with me leading order term. And QI it's plus or minus. So now, all what happened here needs to solve this big system of ODE with one source term, which is related to what happens in the exterior domain. And to solve what happened in this exterior domain, you need to solve this equation with a boundary condition which depend of what happened in the interior domain. So we have finished to write a complete system of equations. It's a complete system with non-local conservative law system with coupled with a big ODE system. Now I will show you how we can simulate this guy, what happens. It work? Not? Perfect. But you don't see? Mm-hmm. Perfect. So if you remember that the difficult part is, if I do some computation, is to compute the pressure at the contact surface between the bottom of the object and the wave. And we try to write this system in order to never compute this difficult pressure. As I show you at the end, the whole system is this one, where I repeat one again that at the exterior domain, we have the waves equation written in the conservative law with non-local flux, which is given by the R1 function, which is what I wrote here with this F, with transmission condition, which is given in terms of variable in the interior domain. It means the velocity of the object and the average of the discharge. And I put here the whole system I write before on the blackboard. And you see it's an added system since I add the equation on the surface elevation, which is an hidden equation here. One remark that I don't want to write on the blackboard, if I see all the coefficient in front of the mean order term, it means the main derivative, the acceleration of the solid, this derivative here, and the acceleration of the surface elevation. You have a big matrix. It is the full added mass matrix. If I neglect dispersion, it means kappa go to 0, then you have something which is the added mass of the solid, acceleration of the solid. If I neglect dispersion, it's deconnected to the average of the discharge. With dispersion, it's not the case anymore, because you see a coupling between both that's involved by the coupling with the trace. So taking into account the dispersion, change the nature of the added mass matrix. And so if you want to do some numerical simulation, as I said yesterday, I consider mesh size of order delta x, and I try to simulate these things. First, if I know at time tn all my shim, the first things to do is to discretize this guy, which is only spatial variable. So at time tn, I just solve R1, which is a very simple shim. And after, I can solve the big ODE on the which is on the big system of ODE, for example, with Euler shim. And at the end, I have my Boussinesq system, which is a type of non-conservative, non-local conservative law with transmission condition, which is given in the term of this ODE, given in this shim. So it is I can put the shim that yesterday I showed you. It's for example here it's a first order Lax Frege system to solve this non-local conservative law with this guy, which is exactly the flux I showed you yesterday. And so just to show one simulation, in the blue here, it's when we solve the wave structure system with the Boussinesq equation, and you will see a curve here in red and blue. If I neglect dispersion, it means shallow water equation, you will see some difference. And with the point, it is the discharge. And for the moment, nothing happens. Now, you see that Boussinesq system is dispersive, so it creates some more oscillation, you see, than the shallow water equation. And here, after, you see that after touching the body, here it will be at a long time, create a shock, and this guy with dispersion regularize this shock. And you can also see the effect of dispersion if I take a very simple case, which is called the return to equilibrium problem. In the linear case, return to equilibrium means that I take for initial condition a fluid at rest and a solid which is dropped on this fluid. And in this case, in the linear regime, it's possible to rewrite the big system of ODE in a very simple case. And we can show that David called the day before invincient damping. It means that in this video, you will see that the solids by dispersion. If I take no dispersion, it's exponentially decreasing. And if I take dispersion, you have something which creates more oscillation, and it's not exponentially decreasing. In fact, it is in a one power law. So now it's depend of time. Yes, I can show you to explain now how we can show this inviscid damping. All the system is very easy in the case of return to equilibrium. It means now I consider in the linear case, it's since it's a return to equilibrium and the body is flat, the initial condition is at rest, so it's completely symmetric, and the transmission condition problem can be seen as a boundary problem because it's completely. So I just write, when again, the Boussinesq equation in the linear regime. Oh, sorry. And at Q is equal plus L, remember that the transmission condition here is only this guy. And the Newton equation is more easy than the last time. It's what it's called the added mass plus delta. Just only the trace plus 2 times derivative of the trace. We only have that. But in the linear regime, it's very much more simpler that in that case, because we have explicit solution of the system in terms of Laplace variable. So I introduce Laplace transform, which transform something which time variable to Laplace, which is by definition. And n is a complex number I take such that this real value is positive. So if I transform this equation in Laplace, I have only I can derive this one with respect to x and multiply, and multiply this one by s to have only one equation on q hat. It will be given by don't do any mistakes. Okay. No, I don't do any mistakes. So it's simply an ordinary differential equation on the space variable. So I can solve it. It has one equation oh, sorry, I don't. Plus the other one. It is very similar to what David showed you for boundary problem in with hyperbolic problem with the Lannes transform. There is one which is non-physical because it's increasing. So you have only this one. You can use now the value of the boundary, which is the Laplace transform of this guy. But this guy have one initial condition, so it is in conclusion, you have, take it at a lemma, the Laplace transform by minus L minus so here we can also know what is now zeta. Which is no, just and here the same. You can plug the expression of zeta in the Newton equation, because here it's 2 times the derivative, and 2 times the derivative is multiplied by a square, and at the end you have one expression in the Laplace variable of delta. So I don't do the computation. The blackboard, you just plug and use it. Right. Oh, sorry, I forgot something. Now, to understand the damping, you must look for the singularity of the transfer function. It is this function here. The singularity of twofold. First, the zero of the denominator, and after it is you have one related to branching point. So if you do some computation, you show that all the zero of the denominator are in this part of the complex domain. And here you have kappa minus 1 and minus kappa minus 1, which are branching points. And so we define a cut where the square root is not defined, which here. So this function is holomorphic in all this domain except this part and the branching cut here. First, if you want exponential damping, you need that the function is holomorphic to one value, one negative value here. It's impossible since this cut is not holomorphing through this cut, so it's impossible to have exponential. But if you analyze very well this guy, we can show there are polynomial damping. So it's the end for the inviscid damping, because I just forgot to say something very important in this case here. I just want to finish by do some comparison between the hyperbolic case that show David and the dispersive case. I do a little summary of what we do in both situations. In the hyperbolic case, I mean when kappa is 0 in the equation, and in the dispersive case, when kappa is strictly positive. David showed you that the solution U, I mean zeta, their regularity structure is given by in time by something that you must pay with spatial derivative. With initial condition, take initial condition in each n plus 1. As I showed you yesterday, it's not the case in the dispersive perturbation. Now, zeta and q are C infinity in time with the same regularity in x than the initial condition. Moreover, in the hyperbolic case, this regularity is satisfies up to compatibility condition. To show this type of regularity, introduce Kreis symmetrizer, and to use Kreis symmetrizer, you use an augmented energy, which is the usual energy, I mean the L2 norm of zeta and q, plus something related to the boundary. And the trace, I have no time to introduce this generalization in the dispersive case. it's not a generalization of the Kreis symmetrizer, but it is the use of the hidden equation on the trace. And when I use hidden equation, I can have also an augmented energy for the dispersive case, but it's not given as a trace symmetrizer, but in terms of the trace of zeta in L infinity norm. So it's something which is bounded by initial condition, and here something, the same thing. But for the moment, it looks better to have a dispersive problem because you don't care about compatibility condition. You can also have an augmented energy, but the problem is here. If I take care of coefficient in the David analyze with Kreis symmetrizer, you can show that the lifespan in the hyperbolic case is at order of magnitude epsilon minus 1, where epsilon is the magnitude of the nonlinearity. But in the dispersive case, if I only use Cauchy-Lipschitz like yesterday, I have something like that. But if you want to take kappa shrink to 0 in order to have the same nonlinear shallow water, to have the hyperbolic problem, you see the lifespan goes to 0. It's not very good. But you can use this augmented energy to perform much precise analysis and try to find the same lifespan. Boussinesq system, I mean not exactly the same, and in other contexts that I show you, I mean a floating structure but which don't move. David and his collaborator Didier Brech and Guy Métivier, show that up to compatibility condition, which are here in terms, they are written in terms of inequality on the initial data. Up to this initial condition, then find a time existent at the same order of the hyperbolic problem. And when kappa go to 0, these compatibility conditions, which are inequality, are the same than the compatibility condition of the hyperbolic problem, which are given in the term of equality on the initial condition. Last things to separate hyperbolic and dispersive problem is that for numerics, to take care of what is on the first cell, the boundary condition, here we use Riemann invariance. In that case, we use the augmented formulation where we couple the hidden equation to the dynamics of the solids. So to conclude, everything in the dispersive case, all the issues are solved with the hidden equation. It's finished for me, and there are 10 minutes more for David. Promise you.
How things behave in the two-dimensional case, so I will just, because it's quite funny and it raises very difficult questions. So that's teamwork. So the idea is that now you look at a cylinder, I take it flat at the bottom, And I want to just to derive in the case of the shallow water equation, so I will write them like this in 2 dimensions. I will, okay, instead, before I was working with the discharge Q, now I write it H times V. V is the average velocity, vertically average velocity. So this is conservation of mass, and this is dTV plus V grad V plus G grad zeta is equal to minus 1 over rho grad the pressure at the surface. Okay, so these are the nonlinear shallow water equation. H, as always, is H0 plus zeta. And as always, we distinguish what happens in the interior domain, which is now a circle in this case. I mean, it could be a cylinder with non-circular basis. It's not important. And the exterior region, which is now a domain which is now it is connected. So we want to transform this system into an initial boundary value problem in this exterior domain, okay? And to find the boundary condition. So as before, I will not do the analysis again. You have P here, which is constant, which is atmospheric pressure, zeta, which is free. And here you have P, which is Pi, and zeta, which is zeta W, and I take it flat, so it's a constant, a negative constant. So as before, the procedure, the recipe is always the same. You distinguish the constraints, and then you give coupling conditions. So the coupling condition of no mass conservation tells you that you have continuity of the normal discharge, which is this condition. Okay, so N here is the unit normal exterior to this circle. So when you cross this the boundary of this zone, you have continuity of this continuity. Okay, so this is linked to this equation, and it tells you that you don't have creation of mass. And then, as in the 1D case, you remember that I had obtained an equation, a boundary condition, a coupling equation by imposing the continuity of the conservation of the total energy, and this led to the continuity of the Bernoulli pressure. So continuity of the Bernoulli pressure is like in the 1D case, and it tells you that pi, which is equal to rho g zeta plus rho 1/2 of q square over, so I can put it with v now, v square in dimension 2 is equal to rho g zeta w plus rho 1/2 of vi, okay, plus pi. Okay, I take p atmosphere to be 0 to simplify. Okay, so now what are is it enough? So the answer is no, because if you look at the equations in the interior region, you recognize this equation, dt zeta I is equal to 0. So you have a constraint. So h in the interior domain is constant. So you have that divergence of vi is equal to 0. And the equation that you obtain on the second equation, this is constant, so this is equal to 0. You obtain dt vi plus vi grad vi is equal to 1 over rho grad pi. So this is exactly incompressible Euler equation, except that you have to impose boundary conditions. You have the boundary conditions that hi of vi dot n should be equal to h of v dot n. This is the exterior domain, and you should have the continuity of the pressure. Pi is equal to pi. So this problem is overdetermined. Okay, if you put an initial condition on vi with the boundary condition, it's okay. But then you cannot impose the pressure or the reverse. Okay, so you cannot impose an initial condition. But then you don't impose the initial condition, you don't have uniqueness. So you can see this, you have non-uniqueness. Because you have solutions, if you take zeta v equals 0 in the exterior region, then you see that you have solutions that are given by vi is equal to a x dot, and you can find pi is equal to minus pi over rho is equal to minus 1/2 of a squared 2 minus x squared minus 1/2 of a squared. You can check easily that this satisfies the equation, and you have, of course, plenty of them. Okay? So you don't have uniqueness. So you have to impose uniqueness, and the way to impose uniqueness, we impose another condition, uniqueness. We impose that we want to work with irrotational solution. So we impose divergence of Vi is equal to 0. Problem is the irrotationality conserved by the equation. This is not obvious because you have an equation for the vorticity, but on an exterior domain and an interior domain with non-homogeneous boundary condition. You don't have Vn equal to 0 here, so it's not a standard case. So you could have creation of vorticity at the boundary. So you want to avoid this and to have conservation of the irrotationality you must impose that you don't have a shear of the tangential velocity. So you have that v dot tau is equal to vi dot tau on gamma. So tau, of course, is the tangential vector. Okay? So what do you have? You have continuity of the normal component of the discharge. Be careful because h is discontinuous. So you have this is continuous, and this in the tangent part is continuous. Okay? Then what is funny is that you can have, in the interior case, now you have rotational of Vi is equal to 0. So you have that Vi is the gradient of a potential function phi. Okay? And from the equation that divergence of h Vi is equal to 0, this is equivalent to divergence of h grad phi is equal to 0. And if you define, so this is an elliptic equation, it is like in the course by Thomas where he had harmonic function. So if you take h constant, it's harmonic. If you take the trace of phi I on gamma and you call it psi, then what do you obtain? You obtain that h I Vi dot n, this quantity, is the Dirichlet-Neumann, I note it lambda and not g anymore, associated to psi I, where the Dirichlet-Neumann operator is the quantity that to psi I associates this quantity. Grad phi I dot n, where phi I solves this equation. Okay? Then what happens? What is psi I? If you look at the equation, you are irrotational. You have dt Vi plus Vi grad Vi is equal to minus 1 over rho grad pi. You can write this as gradient of dt phi plus 1/2 of grad Vi of grad phi square, or Vi if you prefer, plus pi. Okay? In other words, you will have, if when you take the trace of this at the boundary, find that dt psi is equal, this is what I call the Bernoulli pressure, and you understand why I call it the Bernoulli pressure. And since we have continuity of this quantity, we obtain that dt psi is equal to minus pi, which is, I wrote it, pi over rho, which is the quantity that I wrote before. So in order to just to stick in my 10 minutes, just to give you, in the end, the initial boundary value problem that you obtain that you have the shallow water equations in an exterior domain. And then you have boundary condition, which is completely non-standard, is that you have hv dot n on the normal derivative is equal to the Dirichlet-Neumann operator associated to the interior domain, the interior circle, for this operator. And you have, now it's no longer an ODE, you have an equation which is d tip ci plus g zeta plus 1/2 of vi square, of v square, excuse me, is equal to 0 on gamma. So now you have an evolution equation on the interface. Okay? And so this is a funny problem because if you look at this exterior problem, then you have, as in 1D, I told you, the problem is the boundary term in the energy estimate that you have to use Kreis symmetrizers. And here, the boundary matrix, so what we call boundary matrix is AJ NJ, okay, the normal matrix if you prefer. And in this case, it's eigenvalues. So you have 1 plus, you have 1 minus, and you have 1 which is v dot n. So it's the worst case, which is opened from the work of Maida about 50 years ago, where the rank of the boundary matrix can change sign. And in this case, you cannot construct Kreis symmetrizer. This is completely open. But actually, in this case, particular case, there is some kind of very weak dissipativity. So it's not the dissipativity of the Kreis symmetrizer that I showed before. This is a kind of dissipativity. If you integrate in time and in space, you recover something that allowed you to treat this problem. So, okay, so this will be in archive in a few days. We did it with Iguchi. But I just wanted to show you how you can handle this also in 2D. And then in 2D, then you numerically you have to do it. But it's quite funny to see this Dirichlet-Neumann operator appear. And you can imagine if you have in addition the walls are not vertical, then in addition to this, you will have the Dirichlet-Neumann operator, which will depend on the curved surface, and you will have an equation for the surface. But this is enough. I hope it was okay.